Good morning, everyone. Thank you all for taking the time to meet today. My name is Roshan Prashant. I'm a third-year medical student at UWA, and I'm here to present an update on the project that I've been undertaking as part of the Scholarly Activity Unit in the UWA Medical School curriculum. My project is titled Scheduling Metaheuristics and AI for Reducing Radiotherapy Wait Times, also known as the SMART study. Today, I would like to reiterate the background for the project, as well as the key objectives of the SMART study. And then I would like to provide a status update regarding the project at present, as well as some of the key milestones that have been achieved till date. I would also like to describe some of the challenges that we have faced over the course of the last year and the measures that we have taken to address these challenges. And then I would like to conclude by outlining the project timeline from now until the end of the project, which is scheduled to conclude in May of 2025. The overarching aim of the SMART study is to reduce radiotherapy waiting times for cancer patients. Waiting time is described as the interval from when a patient is declared as ready for care by their treating radiation oncologist and the first day of radiotherapy being administered. The clinical guidelines regarding radiotherapy wait times outline a maximum acceptable waiting time of 28 days. And standard good care, in fact, requires radiotherapy to be initiated within 14 days of a patient being declared ready for care. As per the AIHW, which is the primary governing body that publicly releases waiting time data in Australia, the 90th percentile waiting time in WA is roughly 34 days. This exceeds the maximum acceptable waiting time of 28 days for radical or curative radiotherapy, and also exceeds the 90th percentile national data, which is 27 days. Delays in radiotherapy are associated with poorer patient outcomes, specifically in the form of tumor growth, increased rates of tumor recurrence, prolongation of symptoms, and also contributes to patient anxiety. And at present, the pre-treatment scheduling process for radiotherapy is currently done manually. However, there is a growing field in the discipline of computer science known as operations research. Operations research aims to apply an assortment of computational algorithms to optimize workflows. This is widely used across a variety of other industries, such as, with NVIDIA and SpaceX being notable examples. However, instances of this being applied in the healthcare system are sparse, and even more so when it comes to the radiotherapy patient scheduling process. Hence, the aim of the SMART study is to apply workflow optimization on radiotherapy scheduling. And there are three key objectives that we aim to achieve over the course of the SMART study. The first is to apply a branch of workflow optimization algorithms known as Metaheuristics to develop model A. Similarly, another branch of workflow optimization known as reinforcement learning will be used to formulate model B. Both models A and B in the initial iteration of the study were to be applied to a sample of patients who were declared as ready for care across the year of 2023 at Charles Gardner Hospital. The waiting times then predicted by both models A and B would be compared with the real world data for these patients, and this would be a measure of model efficacy. Additionally, both models A and B were then to be used in a cost effectiveness analysis as outlined by Objective C here, whereby the models would explore scenarios where additional resources such as CT scanners and treatment planning systems are procured, and then the change in waiting time would be weighed against the additional costs of procuring this equipment, as well as hiring and training staff to operate these machines. And so this brings me to the project status. Firstly, the radiotherapy patient scheduling, or RTPS, process needed to be mapped to a job shop scheduling, or JSSP, in a job shop scheduling problem, or JSSP, in the field of computer science. Mapping the RTPS and formulating the JSSP is a crucial first step in workflow optimization, as this provides a platform onto which those aforementioned algorithms can be applied to. To convert the RTPS to a JSSP, the scenario needs to be represented as having an n number of jobs, which in this case is the number of patients, that for which there are an m number of machines, which is the key steps in the radiotherapy scheduling process. Each patient has a set O number of operations that need to be completed, and each task takes a P amount of processing time. This was done by first carefully analyzing the radiotherapy patient scheduling process and identifying key steps along the pathway. These are the CT scan for simulation, tumor delineation, treatment planning, and then the role of medical physics as well in the form of conducting checks and quality assurance. Once this process was mapped to a JSSP, A form of the version of metaheuristics algorithms elected for this study was created. The one chosen for the study is known as the genetic algorithm. This algorithm initially starts off with a population of solutions, or in this case, radiotherapy schedules. And these initial solutions are analyzed for their efficacy. The most efficient and effective solutions are selected, and these solutions are paired with one another as parents to formulate a new generation of offspring solutions. The best performing parents and the offspring of each generation are selected for the next cycle. The goal of the genetic algorithm is that over multiple generations and across multiple iterations, this pool of final solutions that are resulted become more and more optimized for the JSSP. Or in the case of radiotherapy scheduling, this pool of schedules become well optimized for the radiotherapy scheduling process. An example of applying a genetic algorithm to the RTPS problem is demonstrated here. This is known as a Gantt chart, where all the machines in the system are shown along the y-axis, time is along the x-axis, and the width of each box corresponds to the duration of each task, and each box itself corresponds to an operation for each patient. This was an example Gantt chart that I developed during the preliminary testing of the genetic algorithm model when applying it to a JSSP. At this point of the project, several of the key initial project milestones had been achieved. The UWA assessments had been completed. A template code with preliminary testing had been completed as well, as shown on the previous slide. And the RTPS problem had, a large portion of it had been mapped to a JSSP. And then we also had a finalized draft of the ethics approval that was ready for submission. It was at this point that we encountered two key challenges. The first of these was with respect to ethics approval. The initial research protocol was submitted to Gecko for approval as a quality improvement project, but we were redirected to submit to HREC with Gecko citing the use of AI as well as the large sample size being the primary reasons for this. Hence, the protocol needed to be revised for the template as per HREC. And so this caused not only delays in terms of obtaining ethics approval, it also had downstream effects in terms of causing delays with formulation of the preliminary testing models that I'd shown earlier. An additional challenge that we did face was with respect to data collection. This preliminary testing model had been formulated by around late July of this year. And it was at this moment that we were actually informed by the radiotherapy department that they were no longer available or no longer able to provide us with the data that was requested for the study. This was unprecedented, given that in previous meetings with the radiotherapy department and the Mosaic teams, we were informed that they could help us with obtaining the data. And so in light of both of these challenges, we needed to obtain an alternative, reliable source of patient data that could be used for the study and for these genetic algorithms. And so a further analysis of the literature actually yielded a study published in 2023 by 3 authors at a Belgian hospital known as Iridium Network. In this study, the authors aimed to minimize waiting times for patients at Iridium Network. And although their focus was more so on optimizing the process of allocating patients to LINACs as opposed to the pre-treatment process itself, this study actually published the distribution of patients by cancer and also published the protocol that they have in terms of prioritizing all the cancers as well. This, in addition to data that could be obtained with the assistance of the radiation oncology and medical physics teams at Charles Gardner Hospital, meant that now we could formulate simulated JSSPs and simulated patient data sets. This now no longer required formal ethics approval. From this data, we were able to formulate early iterations of the model. And the simulation parameters that were used for these early models were as follows. The patient inflow was chosen to be 60 patients per week, and this is as per the radiotherapy department. The patients were distributed across the cancer types as per the study from the Belgian hospital, and they were all prioritized as per the protocol at the Belgian hospital as well. The number of resources at Charles Gardner Hospital was obtained with the assistance of the radiation oncology and medical physics teams. And this model was based on a priority first model where priority A patients would be scheduled first, followed by priority B, and then priority C. So for example, palliative and head and neck patients would be prioritized before cancer and breast and cancer and prostate cancer patients. This is an example of the early iteration of the model where a genetic algorithm has been applied to this simulated data set. As previously, all the machines are listed along here in the x-axis, and the along the y-axis, and the x-axis shows the time of the specific day that the schedule is for. This Gantt chart is a customized schedule for each machine for a specific day, and in this case, it's week 1 Tuesday. The Gantt chart goes from 7:30 a.m. to 5 p.m. every day, and each block here corresponds to a task for a patient at any of these given machines. For instance, patient 26, who has been diagnosed with brain cancer, it undergoes the medical physics check from 9 o'clock to 10 o'clock on week 1 Tuesday. While this model does demonstrate that a genetic algorithm can thus be applied to the simulated dataset, there were 2 key areas of improvement identified. The first of these was that the waiting time of these models was actually found to stabilize or prematurely stabilize in early generations. And this is actually unexpected as opposed to what I'd shown previously with the genetic algorithm, where we expect to see an iterative improvement across multiple generations. The reason for this was identified to be that actually the initial solution that was fed into the genetic algorithm was already quite well optimized, being a priority first model. And so because the initial solution was highly optimized, this did not allow the genetic algorithm with much room to explore the solution space for alternative solutions that minimize waiting times. Additionally, this model had not yet included additional machine-specific constraints, since all machines were available from either 7:30 to 5 p.m. In the case of the CT scan, or from 9 o'clock till 5 o'clock in the case of all the other machines. And so in future iterations of the model, this needs to account for scenarios such as the fact that radiation oncologists have scheduled times during the day where they delineate tumors. And this needed to be variable as per each radiation oncologist as well. So looking at the added simulation parameters that were used for the latest version of the model, these are as follows. Firstly, looking at the resources, the number of treatment planning systems from the previous model were chosen to be 7, even though there are 14 available. Generally, 7 are available on a given day. And on this occasion, these additional smaller steps, such as the treatment planning check, was also included. And so in this scenario, of the 7, 4 was selected for formulating the initial plan, and 3 were selected for conducting the first check. Additionally, the medical physics check was also elaborated on, whereby instead of being just 1 check, there were now 2 checks conducted, one by a junior medical physicist, one by a senior medical physicist, each having different times. And another step was also included, being the medical physics quality assurance that is conducted from 6:30 till before the administration of treatment. Additional data that was included was also cancer-specific timings for the CT simulation and treatment planning. And this is shown in this table here, where, for instance, head and neck cancers have a longer treatment planning time as opposed to prostate cancer. And then future iterations of this model also included the radiation oncologist availability. And this was obtained by looking at the consultant weekly timetable. And as opposed to the initial solutions being a priority-based schedule, the initial solutions were randomized in the sense that each patient was first scheduled to undergo a CT simulation. And then the next step, which is tumor delineation, was done at any available time after the CT simulation was complete, as opposed to immediately after, which is what the previous model used to do. And now looking at the latest iteration of the model, this is an example of the output that is produced from this model. As previously, once again, all machines are along the y-axis here, and time is along the x-axis. And once again, the time spans from, in this case, 6:30 in the morning to account for medical physics QA till 5 p.m. in the afternoon. And this provides a customized timetable for each machine on a given day, such as week 1 Friday. The duration of each box, once again, corresponds to the processing time, and the color of each box corresponds to the pathology for the specific patient. There are 2 key distinguishing factors in this model as opposed to the previous model that I'd shown, the priority-based one. And this is the evolution of the waiting time across generations. As seen in this schedule here, or rather in this set of waiting times here, in early iterations and early generations of the model, the waiting time is significantly longer, being 20 days on average, and the 90th percentile waiting time is actually 38.5, which far exceeds the 28-day limit that is prescribed by clinical guidelines. However, across the multiple generations, by the time we arrive at generation 200, the average waiting time is significantly decreased to 14.72, and the 90th percentile waiting time is decreased to 23.6. So we do see this evolution in this latest version of the model, which we didn't see in the previous version with the priority-based scheduling. An additional distinguishing factor of the latest iteration of the model is the inclusion of penalties. Since the genetic algorithm, it does often introduce errors in the process of crossover, where it reproduces those selected parent solutions when generating offspring. Examples of errors that it can introduce are scheduling 2 patients to be at a machine at the same time, or a patient to be at 2 different machines at the same time. So that's a machine overlap or patient overlap. The randomized nature of this model can also introduce priority violations, whereby a patient with prostate or breast cancer, which is a priority C, is done before a priority A, such as head and neck cancer. For the purposes of demonstration, I have not added penalties for these 3 errors here, but I have added a penalty for order violations, which is another error that can be added by a genetic algorithm, in that a patient can undergo delineation on occasions before the CT simulation, which would not be allowed in a real world situation. And so I've penalized that in the model. And looking at the evolution of that across the generations, we see that in early iterations, the genetic algorithm does introduce this error while it does decrease, while it still has a long waiting time. But as we iterate through the generations, the waiting time decreases and the order penalty also decreases. However, once again, when the algorithm makes a next significant step in decreasing wait time, that comes at a cost of adding more of these errors. But then across further generations, the waiting time tends to stabilize, and the total order penalty then decreases and also stabilizes at a value. And so this brings me to the next step, the next major steps and considerations for this model. These are essentially threefold. The first is to continue to add all these smaller steps that are involved particularly in the treatment planning and approval process. At present, I have included the first plan, the treatment planning check, medical physics check, and medical physics quality assurance as well. The steps that need to be added are the approval time for radiation oncologists, as well as quality assurance from the treatment planning system, from the treatment planning team as well. Additional factors that can be added to enhance this model are including specifically the number of medical physicists, the number of junior and the number of senior medical physicists that are available for the check, and also including radiation oncology approval times, and also ensuring that patients who are diagnosed, for instance, with brain cancers are allocated to radiation oncologists who have a special interest in that field as well. And then looking to automate this process on a week-by-week basis with the new group of patients as they arrive at the hospital. The next stage of enhancing this model is also introducing an error correction mechanism in the genetic algorithm. As shown in the previous slide, the genetic algorithm does introduce errors, which in the real world would not be feasible. For instance, a patient would not be undergoing tumor delineation before a CT scan, since that doesn't take place in the real world. And so adding an error correction mechanism can further enhance this model such that the genetic algorithm, while it may introduce it internally, there's another mechanism that fixes it later down the track. Additional factors that can be considered are also hyperparameter tuning. And so this is altering the specific amount of penalty that I penalize the model by if it does have, for instance, an order violation or a machine or a priority violation. And this can ensure that models that have increased violations are favored less compared to models that try to at least maintain the order of operations while still sustainably decreasing waiting times. Furthermore, more complex cases such as patients requiring SABR may also be integrated into the model. And after this, the genetic algorithm model can explore part C of the study, where it looks to identify the change in waiting time if further resources are procured. For instance, looking at treatment planning systems, seeing if instead of 7 out of 14 are available, looking at the scenario where 14 out of 14 are available, and the change that has to waiting times, or perhaps adding another CT scanner as well. The next area that I believe that we can improve the study by is also by adding another control group. And the reason for this is that in light of the change that has been made to the methodology, to the SMART study, the genetic algorithm is being applied to a simulated patient group as opposed to a real world patient group. And so perhaps implementing or creating a priority only schedule, as I've shown in the earlier iteration of the model, that might be a good control group to compare the genetic algorithm to. The reason being that as previously discussed, with the priority only model, the initial solutions are already well optimized. So that could provide a good control group. And so then looking at the project aims, they have the fundamental aims and objectives of the project do remain, but there are three key changes. The first of these is that as opposed to the genetic algorithm now being applied to a real world patient group, it shall now be applied to a simulated patient group. And due to this first revision, there possibly needs to be the addition of a second control group as well, in terms of looking at the priority only schedule. The reason for this is that while looking at the waiting times of the model and comparing that with the AIHW data provides insight into the possible feasibility of workflow optimization in itself, comparing the genetic algorithm with a priority only schedule will also provide an efficacy of the genetic algorithm itself, more so than just workflow optimization in general. And then furthermore, in light of the sort of challenges that have been present in the last year, as well as some of the complexities of workflow optimization and the genetic algorithm, there are timeline considerations that I have taken into account in terms of the project aims, whereby the focus will primarily be to formulate these metaheuristics models and conduct a cost effectiveness analysis based on this. And only once this is complete, and if there is time available in the project timeline, will the focus transfer to formulating model B, where reinforcement learning will be used. And so this is the revised project milestones. And a significant portion of these have been completed from August onwards. Then, we have all template models finalized, and there are some preliminary results as well for this model. The next steps, as previously mentioned, are hyperparameter tuning and conducting a cost effectiveness analysis and continuing to iteratively enhance this model. The overall aim with all these project milestones is to complete the project and have a finalized manuscript for submission by approximately March of 2025. And this is to allow a 2-month buffer prior to final submission of the research in May of 2025. That concludes my presentation. Thank you all very much for your time. Are there any questions?